In this video lecture, I'm going to answer questions from sample paper number 1, the 4th edition RK Bali navigation book. So let's start. These are the last 10 questions remaining from this sample paper. Compass heading is 090, deviation is 2 degree west, variation 12 degree east, task 160 knots. While maintaining a radial of 070 from a VOR station, aircraft flies a distance of 14 miles in 6 minutes. What is the wind velocity? So let's consider this is the VOR station. Okay, this is your north datum. Radial 070. Your aircraft is somewhere here at a particular heading. The distance is 14 nautical miles. The time is 6 minutes. So distance 14 nautical miles times 6 minutes. So ground speed will be distance by time, that is 14 nautical mile divided by 6 into 60, that is equal to 140 knots. 140 knots. Okay. Now we want to find a final answer, wind velocity in terms of true direction. So let's say this is your true heading, variation, magnetic heading, deviation, compass heading. Correct? So what is a compass heading? 090. Deviation is 2 degree west. Now deviation west, compass will be best, meaning compass direction will be more than the magnetic direction. So magnetic will be less than compass by 2 degree. So 090 minus 2 is 088. Variation is 12 degree east. So variation east, magnetic is least. Magnetic direction will be less than true direction. So true will be more than magnetic by 12 degree. So 88 plus 12 is 100 degrees. Okay. So this is our true direction. Next, we are maintaining a radial of 070 from a VOR station. Now this radial 070 is in terms of magnetic. All VOR radials are magnetic in direction. So let's convert this radial 070 into true direction. Radial in terms of true direction. So again, what is variation? Variation is 12 degree east. Right? So radial will be how much? It will be variation east, magnetic is least, meaning magnetic direction is less than true direction. So true will be more than magnetic. So radial 070 plus variation 12 degree east, that is 070 plus 12 is 082 degrees. So you are actually flying a track of 080 degree true. Okay, this track you are flying away from this VOR station. Your ground speed is this. Your true heading is this. Now we will use CX3 to find out our wind velocity. So go to wind correction option. Now the task given in the question is 160 knots. True course. You are tracking a course or track of 082. You are flying a heading of 100 true. And your ground speed is 140 knots. Is 140 knots. This gives us a wind direction of 158 degree and a wind speed of 51 knots. Okay. So our final answer is wind velocity is 150 degree, correction, 158 degree at 51 knots. So the closest option here is 160 at 50 knots, option A. So 158 degrees approximated to 160 and wind velocity 51 knots is 50 knots. So this is your answer. Bankton, a barometric altimeter using a single static source will over indicate, under indicate, might over or under indicate depending on the position of the static source. So let's say this is your aircraft. Okay, this is your aircraft. Okay, You're going straight ahead, you're flying a direction of north, right? And you have a static port on the left side of the fuselage over here. Only one static port on the left hand side. Now, when you're flying straight and level, you will get accurate altimeter indication. So let's say you're flying at 5,000 feet, you will get your indication of accurate 5,000 feet. Now, when your aircraft banks, let's say this aircraft banks to the left hand side, okay? It banks to the left hand side like this. So the static port which is on the left hand side will get hidden from the incoming, from the relative airflow that is coming from the front. It will get hidden or it will get masked. So the final result of this is that there will be high pressure, there will be high pressure on the right side of the fuselage, on the right side of aircraft, which is exposed to relative velocity or relative airflow coming from the front. Why this high pressure? Because this high pressure is created by the impact pressure of incoming or oncoming relative airflow on the side of the fuselage. So there is static pressure plus there is impact pressure created by this relative airflow. On the other hand, on the left side of the fuselage, the direction in which this aircraft is turning will have low static pressure, or really comparatively it will have lower pressure on the left hand side. Now the static pressure port is situated on the left side of the fuselage over here, and on that left side it is experiencing a lower pressure. So we all know that when we in an atmospheric layer, let's say this is an atmospheric layer, when aircraft climbs in this atmospheric layer to higher altitudes, what happens when you climb to higher altitudes? When you climb to higher altitudes, the atmospheric pressure decreases, which means a decrease in atmospheric pressure is translated into some new information. Decrease in atmospheric pressure equals to increase in altitude, increase in vertical distance. So over here, this static port experiences lower static pressure. This lower static pressure will be interpreted as higher vertical higher vertical distance. So you may be flying level at 5,000 feet, but because of the situation created here, the static port being exposed to lower static pressure, so this lower static pressure will be interpreted as higher altitude. So your altimeter will actually indicate that you are flying at, let's say, 5,500, 6,000 feet, depending on how low the pressure is on that side of the fuselage. Okay, so this is one drawback. So if you have a left static port and left side is experiencing lower static pressure, that is translated into some other information, namely higher vertical altitude or vertical distance information. Now let's say this left static port is not situated on the left side but on the right side. So this static port is now on the right side of the aircraft, on the right side of the fuselage. So what will happen? Now this static port, if it's situated on the right hand side, it will experience higher pressure, more than required. Whereas on the left hand side, there is low pressure, okay, lower than actual static pressure. On the right hand side, we have higher pressure, which is higher than the actual static atmospheric pressure. So now what happens when you experience higher pressures? When do you experience higher static pressures? When your aircraft descends from high altitudes to lower altitudes. So as you come closer and closer to the ground, the atmospheric pressure starts increasing because of gravity. So this higher static pressure is interpreted as lower vertical distance. So what will be the net result over here? High static pressure, high static pressure will be equal to lower vertical distance. That means you may be flying, you may be turning right hand side at a level altitude, that is at a level 5,000 feet. You're not climbing, you're not descending. But the altimeter indication will be such that you're climbing to higher altitude. So maybe you may be flying at 5,000 feet. The altitude indicated to you will be 5,500, 5,800, 6,200, something like that. Something more, correction, it will be lower. So it will indicate 4,500, 4,200, 4,000. Okay. So high static pressure will be interpreted as lower vertical distance. Although you're flying at level altitude of 5,000 feet, the altimeter indication will be much lower than that. So remember, so finally we can say that the altimeter will over indicate or under indicate depending on its position. Okay, if it's located on the left hand side, we have seen what happens. If it's located on the right hand side, we have seen what happens. Right? So the correct answer is option C. It might over indicate, under indicate depending on the position. Conversion angle is the difference between great circle being measured at either meridian, difference between great circle and rhumb line, difference between grid north and true north. So conversion angle is the angle between great circle and rhumb line. So option bravo. Okay, by definition, conversion angle is a half of convergency. I have solved all convergency related questions from RK Bali, Oxford, Keith Williams. So do watch those video lectures. And if you have any doubts, definitely you will get your answers over there. So next, a Mach meter is made up of an altimeter with a density capsule, ASI with an altitude capsule, vertical speed indicator with a modified scale. So correct answer here is a Mach meter is made up of an airspeed indicator with an altitude capsule. So Mach meter indications are nothing but equal to Mach meter indications are nothing but equal to dynamic pressure, which is obtained from airspeed indicator, dynamic pressure divided by static pressure. I have also solved all Mach meter related questions from RK Bali, Oxford, Keith Williams. So do explore the channel. You can find those videos in the respective playlist that I have made. So dynamic pressure divided by static pressure. Dynamic pressure is equals to total pressure minus static pressure. Okay. VMO, okay, maximum operating speed, is calculated based on true airspeed, equivalent airspeed, calibrated airspeed. So VMO is calculated based on calibrated airspeed. Okay, next. In a non-pressurized aircraft, if one or several static pressure ports are damaged, there is an ultimate emergency means for restoring a practically correct static pressure intake. So that means you're flying a non-pressurized aircraft, meaning you're flying at altitudes below 15,000 feet, a general aviation aircraft or some other aircraft which does not have pressurization system in the cabin, in the cockpit. So if you're flying in that particular aircraft and the static port of that aircraft gets blocked, okay, if there is one static port that one static port gets blocked, if there are multiple static sources, all of them get blocked. So what will be the immediate consequence of a static port getting blocked? There will be no input of static pressure to pressure instruments, right? Water pressure instruments, ASI, VSI, and altimeter. All these three pressure instruments depend on static pressure. So if static source gets blocked, there will be no input or no inflow of static pressure in this pressure instruments. So these pressure instruments will get affected, and we all need these pressure instruments for our flight, for conducting our flight, especially ASI and altimeter, right? So if this really happens to you, what is an alternative? What are your options? What are the choices you are left with? What will you do in order to restore static pressure in this pressure instruments from any other thing, from any other source, if you can remember? So the correct answer here will be, you have one option: you can break the rate of climb glass indicator. So the glass or the rate of VSI, excuse me, breaking the rate of climb glass window or VSI glass window will help you restore the static pressure. How? When you break the glass window of VSI, the static pressure in your cabin or in your cockpit, which is nothing but more or less equal to outside static pressure. Why? You're flying a non-pressurized aircraft. So cabin pressure will be equal to outside atmospheric pressure. So now as static port is blocked, if static port is blocked, that means outside atmospheric pressure cannot enter inside. So what you have done is you have opened a new source or a new place or a new entry through which this same static pressure can enter the pressure instruments. Now the new source or the new entry will be your vertical speed indicator. Now like I said, vertical speed indicator is an important instrument for flying your aircraft, especially in climbs, descent, etc. But not as important as ASI and altimeter. Okay, so that's why we make the least risky choice, that is breaking the rate of climb or VSI climb indicator glass window. So correct answer is option alpha. Now if you have alternate static source, you can open that instead of breaking the glass of VSI. Remember, the response time of vertical speed detector may be increased by adding a correction based on an accelerometer sensor. Okay, now our VSI, vertical speed indicator, suffers from VSI lag. This VSI lag is nothing but a time error. As soon as you enter a climb attitude, the VSI will not indicate that climb information, that rate of climb information immediately. It will respond to that rate of climb after a lag of after a after a lag of or a delay of 3 to 5 seconds. So this is called time lag. So this decreases the efficiency of VSI. So in order to increase the efficiency or response time of a VSI, we use accelerometer in it. And this makes a VSI instantaneous VSI. Heading information given by a gyro platform is given by a gyro which is at 2 degrees freedom and horizontal spin axis. Remember? Next. In a low altitude radio altimeters, height measurement above the ground is dependent on what or is based upon what? Frequency modulation, pulse modulation, wave transmission. So correct answer is option A. Low altitude radio altimeters transmit frequency modulated continuous wave towards the ground. It goes to the ground, gets reflected, comes back to aircraft. Now during its journey to and fro, the frequency of this carrier wave will change. Okay, so there will be modulation of frequency for which the frequency variation between the transmitted wave and the reception wave is measured. Okay, so remember, radio altimeters operate by transmitting a frequency modulated radio carrier wave down to the ground. The frequency modulation of the transmitted wave is changed at a constant rate. Okay, by measuring the phase difference between the transmitted and returning waves. Okay, the system calculates the time of travel of the returning wave. So how much time it has taken to go and come back. The wave will have passed from the aerial down to the surface of the earth and back again, which is twice the height of the aerial. Radio signals travel at the speed of light, so the time taken for transmission to return of the signal is divided by twice the speed of light. This is the principle that we apply to all our radar numericals, because always the distance that we will get will be to and fro distance. We are interested only in only one way distance, the distance between your aircraft and the ground. So that's why we divide it by 2. This gives an indication of true height of the aerial above the surface from which the signal was reflected. So remember, it's true height, okay, of aerial, not of aircraft, but of the aerial which is attached to aircraft above the ground. This gives an indication of true height of aerial above the surface from which the signal was reflected. In order to increase the accuracy and to reduce landing impacts during automatic landings, the calculation distance is often adjusted to represent the height of the main wheels above the ground. So very important. Finally, they have made some adjustment in this radio altimeter such that when you get the height readout from this radio altimeter, that height is nothing but the height between your aircraft main wheels and the ground below it. Okay, so this question is often asked in ATPL Viva. So the height indicated by radio altimeter is nothing but the height between aircraft wheels, main wheels, not the nose wheel, main wheels, and ground. So very important. So correct answer will be option A. So that's it. So this ends our lecture. I hope you have understood all the 9 questions that I answered in this video lecture, the explanations I gave. Do watch all the other lectures in which I have solved sample paper questions from other question papers of this RK Bali book. The more papers you solve, the more questions you practice, the more confident you will become, and you will get an idea of what kind of questions are asked in the exam, the way they are asked, the way the questions are framed, and you will also get to know how much time you take to answer these questions. So all the best. If you have any doubts, questions, let me know in the comment box of this video lecture. Best of luck. Share this channel with your friends. Subscribe if you haven't yet. And press the like button if you have liked this video lecture. I'll see you in my next video.